Hello and welcome to this video on true parallel RLC circuits. In previous videos we've looked at series RLC circuits and we've also looked at what we call ideal parallel RLC circuits where a resistor, an inductor and a capacitor are all in parallel with one another. Today we've got a slightly different arrangement, and you can see here that two of our elements are in series. We've got a resistor and an inductor in series, and they're connected to a capacitor which is in parallel. This arrangement is often called a true parallel RLC circuit, and it's called this because it's often used in real life, in real scenarios, mainly in industrial contexts, whereas an ideal parallel circuit is really only exists theoretically. It's very difficult to have an inductor that has no resistance, for instance. And so, for instance, in our example here, we can imagine that these two elements, the resistor and an inductor, are one and the same thing. We can imagine that they're both a motor, for instance. The motor might have some resistance and some inductance, or it might be some kind of coil of wire or other kind of inductive element that has resistance and inductance. So I'm just going to label both of these as our coil, and that could be a motor or similar. One of the great advantages of a circuit like this is by adding a capacitor in parallel, it allows us to perform something called power factor correction and to bring this whole circuit into resonance. This has a number of advantages, one of which we'll see towards the end of this video. Let's begin though by putting some values on our circuit. We can see on the left hand side that it's a 5-volt supply in this instance, a fairly low voltage, but just for example's sake we'll see the principles in action. Let's put some other circuit values on. We'll say that we've got a resistance of 0.2 ohms, so a very small resistance there, and let's say our inductance is 100 microhenries. Finally, our capacitor we'll have as 2 microfarads. The first thing we're going to do, you can see our supply here on the left hand side doesn't have a frequency specified. One of the first things we're going to do is work out the resonant frequency of our circuit. And previously, if you've watched our videos on series resonance, we know that there's a formula for the resonant frequency. F naught equals 1 over 2 pi multiplied by the square root of LC, the inductance, times the capacitance. Now, we can also use this formula in parallel, true parallel circuits like this one. But one of the problems we have is in this true parallel arrangement, as the resistance gets bigger, this formula becomes more and more inaccurate. One thing we can do is we can use a slightly more advanced formula for when this resistance gets bigger. In our case, because we've got such a small resistance, it's probably not going to make much difference, but we'll see how it works out either way. One thing to watch out for though is if you have a question or a problem where this resistance is not negligible, i.e. I can't really ignore it, then it's probably worth using this more advanced formula. And the formula looks like this. F naught, again, because it's for resonant frequency, is equal to 1 over 2 pi multiplied by the square root of, and there's a few things in here, 1 over LC minus R squared over L squared, and that whole lot is under our square root there. So it's a slightly more complicated formula, but we're going to use this slightly more advanced formula. Even though our resistance is negligible, we'll also try and see what we get from our original formula as well. In our case, the results are probably not going to be much different because that resistance is so small. So let's start by using our second formula there, and we can put some values in. The 1 over 2 pi is not going to change. But we then have 1 over LC, and L in our case is 100 microhenries, so that's 100 times 10 to the minus 6, multiplied by C on the bottom as well, which is 2 microfarads, so that's multiplied by 2 times 10 to the minus 6. And from that we're going to subtract R squared, so that's 0.2 squared over L squared, and L again was 100 microhenries, so 100 times 10 to the minus 6, and that's all squared. Just don't forget those brackets there, and that is all under our square root. So quite a complicated formula, but when we plug all of that into a calculator, I come out with a result of 11,249.45, and it's a frequency, so it's in hertz. Just as a little side note, I've also worked out the frequency for our simpler formula here, and that comes out as a frequency of 11,253.95 hertz. And so you can see there's not a huge gulf of difference between our simplified formula and our more complicated, more accurate formula. There's only a few hertz difference between the two, and that's to be expected because this resistance is so small. But as that resistance gets bigger, it becomes more and more important to use our more accurate formula there. So we're going to go with the first result we got there, 11,249.45 hertz. The next thing we can do is we can calculate some values in our circuit. I want to calculate the current that goes through our coil. So I'm going to mark that on my diagram. I'm going to call it I coil. And I'm going to calculate the current that goes through our capacitor, and that's I cap. And there's also the current that supplies them both, and we'll call that IS, the supply current. Let's start by calculating the reactance of our inductor here, this 100 microhenry inductor. And we know how to do that from previous examples. XL is the reactance of our inductor L, and the formula for that is 2 pi FL. We know that our frequency, using our result from before, was 11,249.45 hertz, and we know that our inductor is 100 microhenry, so that's 100 times 10 to the minus 6. And when we calculate all of that, we come out with a result of 7.07 ohms. Now you'll notice that we have two components in series here. We've got our resistor and we've got our inductor, and so together they're going to form an impedance. And what I'll do is I'll call that the coil impedance. So just below here we'll say Z for impedance, we'll call it Z coil. And in rectangular or Cartesian form, or J notation, we can express that as resistance being the real number and reactance being the imaginary, or the J term. And so we'd write that as 0.2 plus J 7.07. Now we can find the magnitude of that impedance by converting it to polar form, or alternatively you can use Pythagoras' theorem. We can say that resistance squared plus reactance squared gives us the impedance squared. But either way, we come out with a result there of not much more than 7.07. Actually, it comes out as 7.073. and that's at an angle of 88.38 degrees. If you're not sure about impedance and polar form, I suggest going back to previous videos where we've covered that, but we've converted it here to the magnitude, and that's still in ohms as well. Now what I'm going to do here is I'm going to discount the angle for now. I'm not too bothered about the angle in this particular question. I just want the magnitude of the impedance, because what I want to do is work out the current in just a second by using Ohm's law. Before we do that though, I want to look at our second branch here. We've looked at the impedance of our coil, but I also want to look at this capacitor here, and that has a reactance as well. And so we can say that XC is equal to 1 over 2 pi FC, a formula that I'm hoping you're familiar with. And similarly, if we substitute the values in there, the frequency being the one above, and the capacitance being 2 times 10 to the minus 6, we come out with a value of 7.07 ohms again. You'll recognize that that's the same as what we got for XL. Now, in a true parallel circuit, be warned that that might not necessarily be the case. They've come out very similar here, and the reason they've come out similar is because this resistance is so small. If that resistance was bigger, it kind of throws these results off a bit. Don't expect them to necessarily be exactly the same, but in this case they are pretty much the same, and we're going to go with that for this example. So now we're happy with our reactances and our impedances in these two branches. We can go ahead and work out I coil and I cap, the coil and capacitor currents. And to do that, we're going to use Ohm's law. So let's begin by calculating the coil current. So what we can do is we can say that I coil is equal to voltage divided by impedance, and in this case we have our impedance Z coil, which we calculated earlier. And so what we can do is we can say that our voltage is 5 volts, and Z coil we calculated to be 7.073, and that was off the previous slide there. Notice we've neglected the angle in this case, but you can calculate it in polar form as well if you want to. But nevertheless, I coil, by doing that division there, comes out as 0.71 amps. And I cap, we can do similarly. I cap voltage over the reactance of the capacitor. The voltage is the same, 5, and our reactance was pretty much 7.07 again. We're going to come out with pretty much the same result, 0.71 amps again. Now, just another warning here, the coil current and the capacitor current look to be equal in this case, and they are pretty much for this example, but it's only, again, because this resistance is very, very small and almost negligible. If my resistance was bigger, these currents might not necessarily be totally equal. That's not the result in all parallel RLC or true parallel RLC circuits. So just beware of that. But in this case, we've got two currents that are pretty much equal in size when we've rounded them to 2 decimal places there. Next, what I want to do is work out the supply current. And the temptation here is to say, well, the coil current and the capacitor current must just add together to give us the supply current. And unfortunately, that's not the case, because yes, these currents we've calculated, but remember, we've neglected some polar form. There's actually a big phase difference between these two currents. Our current here is going to lead by 90 degrees because it's a capacitor, a purely capacitive current, and our current here is going to lag. And so what we can do is we can calculate the supply current by considering something called the dynamic resistance. So what is the dynamic resistance? The dynamic resistance we can think of as the resistance of this whole circuit when it's at resonance. We can kind of simplify and reduce this whole arrangement down to one resistance, but it only happens when we're at the resonant frequency. Fortunately, we are at the resonant frequency. That's what we've been calculating. And so we can calculate the dynamic resistance. The dynamic resistance is a really simple formula. It looks like this. It's RD for dynamic resistance equals L over RC. And if we substitute some values in there, we know that L was our inductance, 100 times 10 to the minus 6. We know that the resistance, in our case, was 0.2. And we know that our capacitance was 2 microfarads, so 2 times 10 to the minus 6. And if I calculate all of that, I come out with a dynamic resistance of 250 ohms. So we can now calculate our supply current, because IS is going to be our voltage divided by our dynamic resistance. And if we do 5 divided by 250, because our supply voltage is 5 and our dynamic resistance is 250, we come out with a supply current that's very small, 0.02 amps or 20 milliamps. So this is very unusual on the face of it, because we have two very large currents in comparison. They're not particularly large, but they're large in comparison to the supply. We've got 0.71 amps, going through the coil. We've got 0.71 amps going through the capacitor, but they're supplied by only 0.02 amps. So this is a very unusual property of true parallel RLC circuits, and you can imagine that it's very, very useful in industry because it gives us great efficiencies. If you imagine, we can have a motor here as our coil. It could be a motor, for instance, and it could be drawing a very significant current, I coil, but nevertheless it's supplied by a very small current, IS, and so we get some great efficiencies. We use less power from the supply and save energy bills and so on and so forth, because we're using this true parallel arrangement to give us a smaller supply compared to the separate currents that we're drawing. And it all comes down to the phase difference between them. They're in a sense cancelling one another to give us a smaller supply current. So this brings us on to one of the key differences between series RLC circuits, which we've looked at previously, and parallel RLC circuits such as the one we're looking at today. In a series RLC circuit, what we saw previously was when we reach a resonant frequency, the current increases. We're decreasing the impedance in the circuit and we get maximum current. And we saw a graph that looked something like this, where we have a peak in current, and the peak occurs at the resonant frequency. So F naught would be here if we have a graph of frequency along the bottom against current up the side. We reach a certain frequency where we get maximum current. If you missed that, it's worth going back to our series RLC video where we cover that kind of arrangement and graph. But in parallel RLC circuits, the opposite is the case. We saw here that we can actually decrease the supply current to something that's very small in comparison to the separate currents that we're drawing in the branches of the circuit. And so what we actually see if we plot IS against F for a parallel circuit is something that looks more like this. We get this dip or inversion in the graph. And so at our resonant frequency, we're actually drawing the smallest current that we possibly can in our circuit. This brings us on to our last little mention in this video, which is on the subject of Q factor. And again, if you missed our previous video on Q factor, it's worth going back to the series RLC videos where we talk about Q factor and what it means. But parallel circuits also have a Q factor, and so the last thing we're going to do in this video is calculate the Q factor for this particular circuit. Now, the formula to calculate Q factor in a circuit such as this, a true parallel RLC circuit, is slightly different. In fact, there's a few alternative formulas that we can use, but the easiest one that we're going to use today is that the Q factor is equal to the capacitor current, I cap, over the supply current, IS. And we know both of these values by now. We said that the capacitor current was 0.71 amps, and we said that the supply current was 0.02 amps. And so if we calculate that, come out with a Q factor of 35.5. Q factor doesn't have a unit, it's just a ratio between these two currents in this instance. So I hope you found this video useful, both on the subject of true parallel RLC circuits and how to calculate some of the parameters within them.